In 1997, Garry Kasparov was beaten by IBM's Watson in chess. Following this event, he invented Centaur chess, or advanced chess. In Centaur chess, a human plays together with a machine. We want to adopt the concept of a human playing together with a machine for design. Through designing together with a machine, designers and machine can work together to develop and conceptualize ideas for the 21st century.
The studio that we are developing within the computational design degree here at UNSW with ARUP, the students are developing a kinetic, adaptable, transformable and responsive pavilion for the ARUP offices. It's almost like a living system because it's going to be capable to breathe, to move, and almost to grow in some occasions. It's going to be sensitive to light, to temperature, noise, and to the human presence. The pod is going to be capable to change the shape, to change the volume of the space within it, to change the permeability of the skin, and adapting itself to the requirements of the office and to the requirements of the users at any time. In that terms, the pavilion is going to be capable to create a small space to do one-to-one consultations or meetings, but it will be capable as well to grow in size and generate a bigger space for lectures, courses, or exhibitions. And in the same way, the skin is going to be capable to change the permeability, allowing to control the entrance of light inside, allowing to create maybe an isolated space from the noise that we have in the office, or another way to make an open area where the visual communication between the office and the things that are happening inside, it's allowed. So what means responsive? Responsive means that all these changes are not going to be activated just with a button. The pavilion is going to be capable to measure the amount of people that is inside of it, how they move inside, the amount of noise that we have outside the office, or the amount of light that we have outside the building. And to do that, to collect all this data, the students are experimenting with different types of sensors. The information acquired with them then needs to be translated in a different type of movements in the pavilion with actuators. So that is the part where I'm going to help the students to, in a way, to transform the theoretical design into a physical prototype. So I'm going to go with them through the process of designing the construction system. So to define how are going to be the nodes, how are going to be the connections between the elements to generate the structure, also how are going to be the mechanisms to open and close the cells of that skin. Each group is experimenting with different mechanisms. Some of them are working with pneumatic elements, others with folding systems, with the properties, the physical properties of the material. So they are working with B-metals as well. And some of them are working with discrete elements that are hanging from the ceiling and they go up and down, creating a kind of a cloud that change in geometry. The collaboration in this studio is going to be done in two different ways. We have the collaboration between industry and university, between ARUP and UNSW. In that way, the students are having a great opportunity to have a first contact with the real world, to translate their academic designs into a real prototype that is going to be built in the office. And I think it's going to be very grateful for the students to see the results in the real life.
Last year, we developed a machine learning framework within parametric modeling environments. And with ARUP, we're going to bring it into the Collaborative Intelligence Studio, allowing kids to explore machine learning within design and directly within the design process. I ran a machine learning module for about a 3 or 4 week period. With the students, we explored this Grasshopper framework, this machine learning framework, and employed it within their designs. Machine learning takes a little bit of linear algebra, mixes it up with a little bit of optimization, and allows computers to extract meaning from immense quantities of data. The main challenge with teaching the students machine learning is the giant gap between architecture and computer science. We had to develop ways to explain machine learning in a highly understandable manner. We've allowed the students to use the neural network tool in any way possible. So I'm really excited to see whether they'll use it for simulation or to actually actuate a kinetic pavilion itself. By allowing the students to have a play around in this machine learning framework, as tutors, we're able to see the potential of human and computer interaction. So the way I see it, and as studies suggest as well, is that the architecture industry is really slow with adopting new technologies. And I think that cognitive computing, machine learning, is a way that we can bring architecture up to speed. With this module, we hope that the students could actually use their knowledge of machine learning, and more specifically neural networks, in their future designs, in their own architectural practices. The machine learning framework that we have is not at all limited to architecture. It's developed in this parametric modeling plugin known as Grasshopper. And so industrial designers, interior architecture, landscape architects can use it within their own fields. From the students' perspective, the collaboration with ARUP has allowed them to receive feedback not just stuck in academia and education. They get real-world responses and input, which helps further them as architects and designers. I've always been interested in thinking computers, how we can make artificially intelligent systems up to human and beyond levels of intelligence. And that just fascinates me.